All right, should look like this. Should look like this. If you want to pin that up on your iPad there. Limiting reactants. Now, magnesium reacts with hydrochloric acid. All right, pretty simple reaction. Last semester in one lab that we did, you might have seen this one happen. Hydrochloric acid. Later in the year, we'll talk a lot more about that. That's the same kind of acid that's in your stomach, and we use hydrochloric acid for a lot of things. All right. Also goes by the name hydrogen chloride. All right. So this is a single replacement reaction. For the test on Thursday, we'll probably just give you all the balanced equations. All right. You won't have to probably do that. I'll have to double check, but I'm pretty sure we'll just give you all the balanced equations straight up. All right. Here's the reaction. If I take some magnesium metal, put it into some hydrochloric acid, it will bubble and fizz, and the bubbles are hydrogen gas. It'll just float away unless I capture them in a container or something like that. HCl is dissolved in water and it makes hydrochloric acid. Hydrogen chloride is dissolved in water and it makes hydrochloric acid. Same thing. All right, now, what do we mean by limiting reactant? All right, in a nutshell, a limiting reactant is the reactant that runs out. All right, it's the reactant that runs out. Now, sometimes it's really obvious which one's going to be the one that runs out and which one's excess, but in other cases, not so obvious. All right. If I got 1.53 grams of Mg and 2.59 grams of HCl, one of those two things is going to run out first, and then the reaction will stop. And that will determine how much product that we get on there. So to figure that out might not be so obvious. If I had 1.53 grams of magnesium and I had 10,000 grams of HCl, which one do you think is going to run out? The one that's really small. All right, might be obvious in that case. All right, but in this case here, maybe not so obvious on this. You look at the balanced equation, 1 magnesium, 2 hydrochlorics, but those numbers are for moles, not grams. So you don't need twice as many grams of HCl as you do Mg, but you need twice as many moles. All right, so you can't really tell straight away just from that fact. All right, if I had 1 mole of magnesium and I had 10 moles of HCl, well, right away I can tell you what the limiting reactant is. All right, so if it's not so obvious, what would I do? All right, generally what you have to do is 2 stoichiometry problems. One would start with the one reactant, and the other one will start with the other reactant. You want to make both stoich problems end with the same thing. One of these 2 products. Doesn't matter which one. All right, could be the MgCl2 or the H. You can pick. You're just going to pick one of those products and do a stoich problem that ends with one of them. Now, it might be better to pick one over the other. For example, look at question 2. How many grams of magnesium chloride should be produced? Since I see that question on number 2, I'm going to pick MgCl2 to end this stoich problem with. And that'll actually answer question number 2 without doing any more work. All right. So if you read ahead, you might avoid a little bit of work by picking the right one. All right. So we're going to do 2 stoich problems. One that starts with the 1.53 grams of Mg. And then we got to do a stoich problem so that it ends in grams of MgCl2. All right, now we've done a bunch of these already. That's one of these long kind of problems. Convert to moles, mole to mole ratio from the balanced equation, convert back into grams. And we can figure out how much MgCl2 we would make if we used up all of the Mg. So all that tells us is how much magnesium chloride we could make if we used up all of the Mg. Now, in that lab that we did the other day, we took a piece of aluminum wire and we put it into some copper chloride. So it's kind of similar type of reaction. In that case, we used up the entire aluminum wire. It's gone. It was all gone. There was none left in the beaker after we let it sit overnight. In which case, we know what the limiting reactant was right away. We'll talk about that lab in a minute, too. All right, now, we haven't answered our question yet. Which one is the limiting reactant? So now we got to start with the other thing. 2.59 grams of HCl. And then we want to do a stoichiometric problem that ends with the same thing, the same compound. Convert to moles, mole to mole ratio, convert back to grams. The blue numbers I got from the periodic table. Molar mass of magnesium, molar mass of HCl. I'd have to calculate those on the fly. Usually we end up with 2 decimals. This might have been using a more precise periodic table. The whole numbers in the mole to mole ratio, those came out of the balanced equation. Usually when we balance equations, we don't write ones in there, but if we do, it's not a problem. It's useful when doing stoichiometry. Again, anything on the top, multiply by it. Anything on the bottom, divide by it. If you haven't tried to do one of those in a calculator yet, you definitely should today, because there are spots where you can make an error on the calculator. Remember, don't use any parentheses when doing the calculations. Not necessary. Just multiply by anything on the top, divide by anything on the bottoms. All right. At this point, we know which one is the limiting reactant. Sophia Larson. Which one is the limiting reactant? Now, it's not this, because that's a product. The reactant is the thing in the front. All right? So the HCl is the limiting reactant. And the reason is that will make the least amount of product. So when that runs out, we'll get 3.38 grams of magnesium. All right? If we used up all the magnesium, we'd get more, but the limiting thing is going to tell us how much we actually do get. All right? So that answer tells us what the limiting reactant is, but that is not the limiting reactant. The limiting reactant is the thing in the front. It's the thing in the front. All right, so if the question was, what's the limiting reactant? Well, you'll have to do 2 stoichiometric problems, and this is not so obvious. Whatever one gives you the least amount of product, and it doesn't matter which product you pick, that will tell you which one's the limiting reactant. Now, there's other ways to do it, but it amounts to the same amount of work. All right, I could use one and find out how much of the other one I need, and then compare it to how much I actually have. It's the same amount of work. All right. So this is what we got to do to determine what the limiting reactant is. All right, what is the limiting reactant? It takes 2 stoichiometric problems. That question students report as being the hardest thing that we learn all year in chemistry. All right, what's the limiting reactant? All right, because you have to do a lot of stuff. You got to calculate a molar mass. You got to set up the problem. You got to punch it into the calculator correct. You got to round the answer in the right spot. You got to do pretty much everything we've learned how to do up to this point, for the most part, on there. So, which is the limiting reactant? You do 2 stoichiometric problems. Our reactions will always start with two reactants. We won't throw in one that has three or four like that. If we have a one reactant, a decomposition, then a limiting reactant's really not a issue because it's the only reactant. All right, so for us, it's always going to be a 50-50 guess. All right, if the first question said, what's the limiting reactant? Well, if I pick this or that, I got a 50-50 chance of picking the right one. All right, as long as you know which ones are reactants. If you, of course, pick MgCl2, that's not even a reactant, that's a product. All right, so that's how we determine it. You got to do two full stoich problems. Now, if we started with moles and we wanted to end with moles, then it just makes the problem a lot shorter. You only got to do one step, basically. All right, now, question number 2. How many grams of magnesium chloride should be produced? We call that the theoretical yield. All right. Now, since we picked MgCl2 to try to figure this out, we already got the answer to that question. What's the answer to that question? Judah at home? What's the answer to number 2? You got it, Judah?
5.99.
Nope. It's the other one. See, because the HCl is going to run out first, and that's all that we can make. Right? If the magnesium ran out, we would make that much, but we can't make that much because this is going to run out first. The HCl is going to run out first. So the answer is that right there. All right, that's all we can make. The limiting reactant runs out, that's how much we can make. So we already answered that question. Now, if we would have picked H2 to make, do this problem to end with, then we would have to do that problem over. Then we'd have to do the problem over. So if you read ahead, sometimes it helps eliminate a little bit of work. So number 2, we already got the answer. We don't have to show it again if you already did it. So that's how much we would make. We call that the theoretical yield. That's how much you should get based on if all of that gets reacted. All right, that's how much you should get, theoretical yield. So theoretically, if all the HCl gets used up, you should be able to make 3.38 grams of magnesium chloride. That's what it says. All right. Now, in our lab that we did, and we'll look at it again here, we took a piece of aluminum, we put it into a solution of copper chloride, and the aluminum completely disappeared. So that determines how much copper you should get. All right, that determines how much copper you should get. Now, you might not actually got that. So let's say we actually did this experiment and we were expecting to get 3.38, but we actually only got 2.96. We'll call that the actual yield, what you actually get. All right, then we got a formula. If you take the actual yield, what you do get, divided by what you should get, times 100, you'll get a percent. You'll get a percent. We call it percent yield. Now, why would you not get 100%? Well, there might be lots of reasons. In the case of the lab that we did, remember you made some copper and then you poured the stuff into the filter. Some of the copper might still be stuck on the side of that beaker and never made it into the filter paper. That would cut down on your yield. So there's different reasons why you might not get 100%. Another reason might be in the lab, we started with copper chloride dihydrate, so we're thinking that every molecule has water stuck to it. That might not be true. That's going to affect your yield. So if they're not all hydrated, then you actually have more copper chloride than you think you have. You might end up with higher than 100% yield. So sometimes you can go over, sometimes under. There's lots of different reasons. All right, that right there is a limiting reactant problem. All right, you got two reactants. You got to figure out which one is the limiting reactant, the one that runs out. And then you got to figure out how much you should have got based on that and compare it to maybe what you did get, and then find a percent yield. On the test next week, you'll probably definitely have a problem that has all of this in it. You gotta start with a couple things, figure out what's limiting, figure out your percent yield, and so on. All of that. In the lab that we were working on here, we do all that. Let's take a look at that. All right, let's take a look at that. All right, that's limiting reactants. All right, so number 3, let's review the lab calculations. A lot of people send me messages that I'm confused on doing the calculations. I haven't Dropboxed it yet. That's fine. If you did Dropbox it and you got it all set and everything, then good. All right, let me find the right spot on my thing here. All right, let's review the calculations in the lab. Now, on Schoology yesterday, I put the hints to the calculations. It included all that pre-lab stuff that we already did. All right, notice one of the questions here, number 5. What is the limiting reactant? That's the reactant that runs out. Our data table should have everything in it now. We took copper chloride, dissolved it in water, put a piece of aluminum wire in there. Copper got made, sank to the bottom, poured it through a filter paper, let it dry out, found the final mass. All right, calculations. You got to have a balanced equation. If you don't have that down there yet, that's what it is. This is aluminum was that little piece of wire, and the copper chloride was the blue crystals that we dissolved in water, and then we threw the wire in there. In question 2, all we're doing here is figuring out how much CuCl2 we actually used without the water hooked to it. So that's why we did this step. That's one of your starting reactants. Now notice question 3 and 4. It's the same thing that we just did right here, limiting reactant. Pick one of the products. Well, one of the products, we're going to pick copper because that's the product that we're trying to make. We're going to take the copper chloride that we started with, figure out how much copper we should have made. Notice the should is in bold. How much you should have. Now we got a stoich problem here. And we're going to figure out how much copper we should have made. That's in your filter that dried out, that last thing you weighed. That's how much copper you should have got theoretically. And then we did a stoich problem with the aluminum. That was the first thing you weighed, the mass of the aluminum. Do a stoich problem, end with copper as well. From those 2 questions, you can figure out what the limiting reactant is. Well, in this case, we already know it because the wire is gone. The aluminum is gone. So it's the limiting reactant. So which of the reactants is the limiting one? It's going to be one of these 2 things here. All right, let me show you the calculations with my data. Yours will be a little bit different. All right. So I measured out 2.58 grams of copper chloride dihydrate. Went a little bit over 2.5, but it said approximate. And then I calculate, this is how much I got. So now I'm going to do a stoich problem and see how much copper will I make if I used up all of the CuCl2. That's how much copper I should make if I use up all of that. And then I do that same thing with aluminum. I start with the mass of the aluminum wire, figure out how much copper that should make. From that, I can see that the aluminum is the limiting because it would make the smallest amount of copper. So when it runs out, that's how much copper I should have. That is my theoretical yield. That's how much I should make. The excess copper chloride, that was just in the beaker, and then we dumped it down the drain. All right, which one's the limiting reactant? We're going to say aluminum. All right, now it's not copper, that's a product. Go back to the front. It's the aluminum that is the limiting reactant. And we knew that because the aluminum ran out. We saw that. But we could prove it by doing stoichiometry here. All right. The rest of it then is calculating that percent yield. The percent yield. You got your theoretical, you got the actual, the stuff that you actually measured. Now the actual mass of copper is on your data table. It's the last row on your data table. That's the mass of the filter paper with the copper in it. Subtract the mass of the filter paper and you'll get the mass of the copper that you made. That's your actual yield. All right. So we'll need that to figure out the percent yield. Percent yield. All right. Question 8 says, suggest reasons for not getting for getting something other than 100%. Now, usually you end up with less than 100%. And the main reason might be that some of your copper's still stuck on the side of the beaker when you poured it into the filter. That'll cut down on your percent yield a little bit. If you want to write that, that's all you need to write. The last extension question, just another stoich problem. All right. That's the